Now let's summarize CSMA. In CSMA, finally you realize that when there are multiple stations and you have a common medium, you have a problem. What is that? How data can be sent, correct? So when you use CSMA protocol, then stations are going to use a capability called sensing, right? So whenever a station sends the channel before sending the data, such protocols are all called CSMA protocols. Okay. Now in CSMA protocols, let's say your stations are sensing the channel, right? Example, let me ask you one question. How station A sends the data? I'm asking how station A is going to send the data into the medium, correct? So you have now sensing capability, that is what CSMA. Okay, using that you are sensing it, but already I told you that. So station A is going to sense this channel. If this channel is idle, then it is going to send. If this channel is busy, then it is going to keep quiet, correct? So and it will be keep on sensing. One day what happens, your channel will be idle, at that time station will send, correct? That is the usual procedure, that is a common procedure, that is called one persistent technique. Okay, so finally how your stations are going to send the data is the question we have. So to answer that, we have techniques in CSMA. They are called persistent techniques. In persistent techniques, you know already one persistent. Let me revise. One persistent technique is nothing but whenever station A has data, it is going to sense the channel. If the channel is idle, it will immediately send the data into the channel. If the channel is busy, it is going to wait. By keep on sensing the channel, it will wait. One day what happens, otherwise after some time, so definitely your channel will become free, correct? So immediately again your channel will your station will send the data. This is called one persistent technique, already we have seen. Okay, so the second one is we have other alternative, that is no persistent technique. In no persistent technique, what we are going to do, if you want to understand, first of all you should try to understand what is the problem with one persistent technique, what is the drawback of that, we will see. The drawback of usually one persistent technique is, see, when channel is, let's say, busy, what your station is going to do, it is going to wait, correct? Now let's say at the same time channel station B is also sensing it, then both will feel that there is a signal inside it, okay, because channel is busy. Now see the scenario, after 5 minutes, let's say your channel become free at a time, because both are sensing, right? Because everyone is waiting. So station A and station B will be waiting and they will be sensing. Suddenly they feel that your channel or medium is free. So whenever they see free channel, what they do, according to one persistent technique, they immediately send. If really there are multiple channels, sorry, multiple stations who have data, then immediately they will start sending, right? If they follow the same technique, one persistent, every station which is now currently having the data, at a time they will see the channel empty, then they will send. Now what happens? Collision. Whenever there is a collision, so what they do, that is not, given in CSMA protocol. So we are going to learn CD, how collision can be detected and how to solve that problem, we will see at this moment. So we just understand in CSMA how we can send the data. If collision occurs, what happens, we will see that later. Okay, so at this moment only CSMA, only sensing and sending. Now so this is about one persistency problem. That's why to solve it we have no persistent technique. In no persistent technique, what we are going to do is, so we are going to solve this problem rather than immediately sending. What channels are what stations are going to do, I will tell you. Let's say station A has some data, okay, let's say some data D1, and station B is also now having D2. Now in no persistent technique, stations first of all they will sense the channel. If this channel is idle, what they are going to do is they are going to send as usual. That means no persistent is equal to one persistent whenever your channel is free. What if this channel is busy? When this channel is busy, then rather than waiting, so these stations are going to wait for some random time. Okay, so let's remember this concept, random time. So every station is going to, generate a random number. Based on that number, they are going to wait. Okay, so after random time, now stations will again sense the channel. If they see the channel free, they will send. If the channel is again busy, then again they will wait for random time. So that technique is called no persistent technique. That means we are not immediately sending, we are postponing our decision. Understand? So this is about no persistency. Understand? Okay. Now, sir, how this random time will be decided? Usually, this random time will be decided by protocols. We can discuss on that. Example, let's say we can keep a transmission time. That means that random amount of time they can fix, like transmission times, 1 transmission time, 2 transmission times, 3 transmission times, in that way. Example, let's say station A, station B wants to send the data and they felt that channel is busy, so they are going to generate a random number. Example, let's say A generated a random number 1, B generated a random number 2. Then so station A is going to wait for 1 into frame transmission time. Assume that, so these stations are having some rough idea about what is the average frame transmission time. Let's say in this channel or in these systems, so we assume that, let's say every station is sending fixed size frames and the frame transmission time is 2 seconds. Then if station A generates random number 1, it will wait for 2 seconds. Now if B generates a random number 2, then it will wait for 2 into 2 seconds. So that's why, so A comma B both are going to wait in different times, correct? That's why, so there will not be collision next time. There is a very low chance of getting the collision. What happens, we'll see. After 2 seconds A will try, after 4 seconds B will try. That's why at a time they are not trying. Understand? After trying at any time, remember, again if the channel is busy, then they are going to wait for again some random amount of time. Understand? That random amount of time is not constant or same, right? So that depends on the system. In that way, so no persistent technique can be implemented. Now these are all ideas, okay? Just learn the ideas, that is enough. So exact things will, not required, and there is no exact thing. Sir, is it really transmission time or anything else? Yes, it can be propagation delay also. Sometimes we can use propagation delays or some other parameters also. That's why that random amount of time is highly depending on the strategy which is used by some protocol. That's why don't worry about it. Only learn the idea. Now let's summarize these two ideas. In one persistent technique, every station, whenever station is busy, they will wait and they will keep on sensing, and whenever they get chance, that means whenever this channel becomes empty or free, immediately they send. That is one persistent. Now in no persistent time, whenever channel is busy, stations are going to wait for random amount of time and again they are going to send the channel. Now this will be repeated. Now we'll see third technique, that is P persistent technique. In P persistent technique, what we are going to do is, it is, I can say, a middle point of this one persistent technique and no persistent. It will have advantages and disadvantages of both models. So what is that P persistent technique? We will see. Let's see P persistent technique. In P persistent technique, assumption is, let's say your time is slotted. That means now the time period is divided into some slots. Okay, only at beginning of the slot anyone will try. Okay, so let's begin that story. In P persistent technique, first of all, every station senses the channel. When a station has frame and channel is free, assume that, let's say channel is free, by sensing it will understand, correct? Because it is CSMA technique. Now whenever channel is free for any station, then what that station is going to do is, so there will be a probability called P. Using that probability P, I will tell you how to have calculate probability value. So with some probability P, frame will be sent. That means what? I will tell you. Example, let's take one probability 25%. That means 1 by 4. Example, let's say station is using 25% probability, then it is going to generate a random number between 0 to 4, 0 to 3. Example, try this one, 0, 1 to 3. How to imitate this probability I am telling now. That station is going to generate a random number between 0, 1 to 3 using some subprogram. So let's say at this moment, let's say, if let's separate like this, 0 is one case, 1 to 3 is other case. See, what is the probability that your random number is going to be 0? 1 by 4. What is the probability that if random number is generated between 0 to 3, that is going to be 1 or 2 or 3? Definitely 75% chances we have, right? 3 by 4. So now whenever a station wants to send a frame and channel is free, then with probability P, station is going to send the frame. That means if probability is 25%, then with 25% probability, it is going to send the data. To generate that kind of probability, that means to have that kind of probability, it is going to generate a random number. Example, let's say whenever random number is generated, let's say it got 0. If it gets 0, that means what? That is 25% chance. That means, so it is now success probability, correct? Then immediately, so 0 comes, then it is going to send. And if 1 or 2 or 3 is generated, then it is going to take the other decision. We will see that also. Okay. Now, whenever 0 comes, then your station is going to send the frame. Perfect. Now, read the statement again. What I said, whenever station has a frame, it will sense the channel. If the channel is free, then it is going to generate a random number like tossing the coin. So, output will be 0 or 1 or 2 or 3. If 0 comes, we know that 0 comes with 25% probability. That is what P for us. In our problem, P persistent technique uses this P. So we use that 25% as the probability. With that, we are going to send now. Now let me ask one question. What is the probability that you are going to get 0? Whenever you get 0, then only you are sending. The probability for getting 0 is 25%. That means with 25% probability, this station is going to send the data. Now, what if 1 or 2 or 3 comes? Then that has 75% probability. With 75% probability, which is 1 minus P, let's read the statement. With probability 1 minus P, the sending will be postponed to next slot. That means, so with that 75% probability, we are going to postpone the decision. Up to what time? To next slot. Example, let's say this, I will tell you how to fix a slot. At this moment, let's say, assume that, let's say we can fix the slots. So this slot is done. We didn't get chance. Then we will go to the next slot, and already I told you that you know how to synchronize your receiver so that I can say that your system, so that we will exactly find out the beginning of the slot. We will find out the beginning of the slot. Then again we start sensing. Now this time again your channel is, let's say, free. If the channel is free, what we are going to do, you see. Now with probability 1 minus P, we are going to postpone to the next slot. We will go to the next slot. And then channel is again sensed. If channel is free, then go to step number 1. Do the same whatever you did. What we did, whenever the channel is free generally, then generate the random number again. Now, sir, again if 0 comes, simple. If 0 comes means we know that with 25% probability it will come, then the decision is with the probability P you are going to send. That means if 0 comes, simply send it. What if 1 or 2 or 3 comes? If 1 or 2 or 3 comes, then definitely we'll come to the second case. That means the sending will be postponed. That means again we will postpone to the next slot, and again we start sensing. So now idea is very simple. Whenever you want to have P probability, that means whenever you want to send your data with P probability, let's identify that value. If you want to send with 25% probability, then just generate a random number between 0, 1, 2, 3. 0 means, let's say, success. 1, 2, 3 means failure. That means postpone your sending. So now let's start. Let's imitate this procedure for one example so that you can easily understand. Now, let's say in the early morning, let's say station A has data. It will sense. If channel is busy, then simply what we do? See here. Whenever station has, channel is busy, then we simply continue sensing. Suddenly channel will become free. Whenever channel is free, now story begins. Understand? Whenever channel is free, generate the random number. What if the random number is 0? Then that means what? Simply we assume that, let's say, coming 0 is nothing but now probability having probability P, correct? So that's why we simply send the data. What if 1 or 2 or 3 comes? Then go to postpone, go to the next slot. Wait for the next slot. Now next slot will come. Now again sense the channel. If channel is busy, keep sensing. Suddenly channel will become free. Whenever channel becomes free, then again same story. What we have to do? With probability P, we should send the data. For that, generate the random number again. This time let's say 0 comes. Then send it. Sir, what if 1 comes again? Yes, it comes sometimes. Then again go to the next slot. Sir, what if every time always 1 comes, then your fate is bad, correct? Very rarely it happens. So what generally we do is, every time if one comes, then we try 20-30 attempts. Okay, so after 20-30 attempts, so whatever may be the case, just simply send it out. Okay, it's not the particular strategy. There can be so many different strategies possible, but this is a rough idea. Okay, now after 100-200 times still you are not able to send, then we maintain a counter and we realize the situation. It is a exceptional situation. In that situation, we take some random decision which favors us. That means which favors the station. In that way, P persistent technique can be implemented. Understand? Now one more thing, in GATE exam, so if they ask any question related to P persistent technique, definitely they mention the definition and they mention the actions, everything. They never ask a question, which is whenever, see, actually this is an idea. It's not a perfect idea. That means, this idea can be executed in so many ways. When there is ambiguity, then in GATE exam, they don't ask a question. They ask a clear-cut question. So here now, so really they want to ask a question, then they will clearly explain you what is P persistent technique, everything. Otherwise, they ask a question so that there is no ambiguities, anything. So there they ask a question. That's why you understand the basics, then that is more than sufficient. And we are learning more than the basics. That's why any GATE question we can answer. Understand? Let's learn binary backup algorithm. I will tell you where we use binary backup algorithm and how this algorithm works, everything. Okay. So before that, so let's summarize CSMA CD. You know what is CSMA, right? So using some persistence technique. So we are going to send the data. Already I told you what is persistence technique, right? Using some persistence technique, let's say you are sending the data. That means every station applies one persistent technique. Maybe that is one persistent technique, then immediately they send whenever channel is free, and maybe non-persistent, otherwise P persistent. Whatever it is, so they apply that procedure, and finally, let's say A got the chance. Let's say finally A started sending the signal. That will be taken care by the CSMA. Already I told you how the CSMA works, right? Now let's say A started sending. Now because of collision detection, so definitely your station is going to detect the collision whenever there is a collision. How, sir? Because we are going to have a condition that transmission time is greater than or equal to 2 into propagation delay. Already I told you. Such a way we are going to have longer frames. So whenever you are sending that kind of longer frame, if in the worst case this D kind of station that station also sends the signal within 2 into propagation delay time. In this time we are definitely going to feel the noise in the channel, right? So that's why that is what collision detection technique. It is very simple. So collision detection technique says that, my dear station A, you keep on sensing while sending the data. Send the data, sends the channel. Send the data, sends the channel. Since your transmission time is greater than or equal to 2 into propagation delay, if and all if there is a collision, that will occur before this much time. That's why, so while sending the data, if you don't sense any collision, definitely there is no collision. Understand? That is what collision detection technique. Now let's say finally, let's say some channel some station got some collision. What they are going to do? So A and B are involved in the collision. So what they are going to do? Definitely they have to wait, correct? So immediately after so let's say there is a collision, A stopped and B stopped. Immediately if they start sending again, there is again a collision, correct? So that's why what is one important strategy is this station A and this station B has to wait for some random amount of time. Okay, so A comma B stations are waiting for some random amount of time. Usually we implement this model. Try to understand. Let me summarize. Whenever two stations are involved in the collision, sir, if there is no collision, nothing. If there is a collision, then so these stations are going to wait for some random amount of time. So how this random amount of time can be calculated? Do we have any procedure? Yes. That is what binary backup algorithm. Using binary backup algorithm, we are going to decide each station and how much time they have to wait before sending the data again. Let me summarize it again. Multiple stations are using the persistence technique, whatever it is, they are going to acquire the channel, right? So whenever they somehow realize that this is their turn, they will start sending the signal. Already I told you, like, in that P persistent technique or non-persistent technique or one persistent technique, so there is a method to send the signal, correct? Finally, so multiple stations started sending the signals at a time using that technique. What happens? Collision will occur. Then using the collision detection technique, we are going to find out that collision detection is very simple. Every station has to send the data at the same time. While sending, it should sense. Understand? Then definitely they will detect the collision. So once collision is detected, then they have to wait for some random amount of time. That random amount of time is going to decided by this algorithm called binary backup algorithm. I am going to teach that. Okay. Now we'll see binary backup algorithm. I will explain binary backup algorithm with considering two stations. So we can extend that to multiple stations. That means you can understand this idea to multiple stations also. Okay. So it is easy for us to understand with first of all two stations. Let's begin it. So let's say station A, station B. So we use a variable called K. Using that we are going to decide the waiting time. Okay. So let's try to understand that slowly. So initially K value 0. Now station A, station B are going to, whenever they have data, immediately they will send. What if there is a collision? That is a story. If there is a collision, we run this algorithm, binary backup. Assume that, let's say, there is a collision. If there is no collision, nothing. So, after collision, when they detect it, they will stop sending the remaining frame, whatever they have. Remember it. So, in the CSMA CD algorithms, whatever, so whenever a station sends a signal, and if it realizes that there is a collision, then immediately such station will stop sending it. Immediately. Okay. So remember it. Now A comma B both will finally sense that there is a collision, they will stop. Now they will go to this mode, binary backup algorithm. In that, so they will increment this K value. Initially K is 0, right? So since it is a first collision, then K will become 1. Now A is going to generate its own random number which is between 0 to, I can say, 2 to the power of K minus 1. That means 2 to the power of 1 minus 1. Remember it. So here station B is also going to generate a random number between 0 to 2 power 1 minus 1. Since K value 1 for this one also, right? So both will have same value. Now what happens? So A is going to try a random number between 0 to 1. B is going to generate a random number between 0 to 1. Now see. So there is a possibility that A might get 0. B might get 1. What is the meaning of that? I will tell you. If A gets 0, what does it mean? If A gets 1, what does it mean? I will tell you. So they are going to wait for some random amount of time that is going to be decided by this K value. Okay. Now, if K equal to 0, then such system is going to wait for 0 into, so this 512 bit transmission time. So why this weird number we will see in Ethernet? Okay, so generally this 512 bits is specially for Ethernet, but we can fix anything. I am taking, let's say, 512 bits. Why I am taking 512 bits? I will tell you, because we are going to study Ethernet. In that Ethernet, we are going to have this number, but generally that will be 2 into propagation delay. Understand? So one round trip time generally they decide. Let me decide some number here. That random amount of time is transmission time of exactly 512 bits. For good understanding, assume that, let's say, this channel's bandwidth is 10 Mbps. If the channel bandwidth is 10 Mbps, then to send 512 bits, what will be the time? Definitely message size or frame size 512 by 10 into 10 to the power of 6 bits per second, isn't it? Then if you convert it into seconds, what happens? It will be 51.2 microsecond, right? But why this 512 bits transmission time we will be learning in Ethernet. Just remember it. So station A is going to generate either 0 or 1. Similarly, station B is also going to generate 0 or 1, right? Now assume that, let's say, A got 0. If A gets 0, then 0 into 51.2 microsecond. That means A is going to wait for 0 seconds. What if B gets 1? Because it is going to generate a random number between 0 and 1. So with 50% probability, it might get 1, right? At that time, so it is going to wait exactly 1 into random amount of time, which is 51.2 microsecond. So A is going to immediately send and B is going to send after 51.2 microsecond. So our assumption is, so meanwhile the transmission or propagation of A is done. So that is the way we plan it. Now while studying theoretical idea about binary backup algorithm, then we just take random amount of time as something, whatever it is, don't worry about it. But in the GATE exam, if they give any question, they will mention what is random amount of time. Second one, when you are designing one technology like Ethernet, we are going to study Ethernet. Now on that we will see based on the situations and circumstances and some of the limitations we have. With that we are going to fix that random amount of time. Okay, so at this moment of time, remember that we are using 51.2 microsecond, but most often people use 2 into propagation delay for that random amount of time. Okay, you know the significance of 2 into propagation delay, correct? It's a round trip time. So remember that point. And now what if again A gets 0, B gets 0? Because it is randomness, right? What if A gets 0 and B gets 0 in the first round of this random number generation? Then both will try 0 into 51.2 after 51.2 microsecond into 0. That means immediately. When both will try immediately, then again there will be a collision, isn't it? Then what happens this time? So their k value will be increased. That is the idea about this binary backup algorithm. So this time, so k equal to 2, then this time 0 to 2 power k minus 1, 2 square minus 1. In this interval, random number will be generated. Since k also is involved in this collision, right? So k value of b also will be incremented to 2. Then this time it is going to generate a number between 0 to 2 square minus 1. That means A is going to generate a random number between 0, 1, 2, 3. B is going to generate a random number between 0, 1, 2, 3. Assume that let's say this time A generated 2 and B generated 2. Then what happens? A is going to again send its data after 2 into random amount of time. That means 51.2 microsecond. So B is also going to send data at 2 into 51.2 microsecond. Then they are going to involve in one more collision. But I want to say that there is a rare chance. Why? So what is the probability that, so both are going to pick same number? We will see. What is the probability that both gets 0 and 0? It's very easy. I will tell you. Let me ask one straight question. What is the probability that A is going to generate 0? Because assume that let's say that random number generator is good and it is, I'm assuming uniform distribution. Whenever I assume uniform distribution, then every digit will have same chances. Then out of 4 chances, 0 will have 1 chance, 1 by 4. That is just assumption. Now here also, let's say random number generator is very good and it is uniformly picking the numbers, then the probability that 0 is selected here is 1 by 4. Now 0 should be selected here, 0 should be selected. What is the probability that event number 1 occurs here and event number 2 occurs here? What is event number 1 here? Getting 0. Here let's use same even. What is the probability that event number 1 occurs? Same. They are independent. A's random number generator is different and B's random number generator is different. Otherwise, whatever the random number generator, so these two events are independent. Getting here 0 and getting here 0, right? We know that in discrete maths also I taught you that, correct? So that's why what is the probability that they are going to have 0, both are going to get 0, 1 by 4 into 1 by 4, right? Remember it. But there is another chance to get the collision. What is that? A gets random number 1, B gets random number 1. Again they are going to try after 1 unit of time. Then they are going to get the collision. But probability again same, right? 1 by 4 into 1 by 4. Let's mention it. Next, similarly for probability of getting 2 and 2, 1 by 4, 1 by 4. What is the probability that both gets 3, 1 by 4, 1 by 4. Now to occur collision, either they should get same 0, otherwise 1, otherwise both should get 2, otherwise both should get 3, correct? If they get 0, they don't get 1. If they get 1, they don't get 2, correct? That's why all the events are mutually exclusive. Very simple. We have to add these probabilities. I will tell you why we are adding. Every event, see what is this event? This event is nothing but getting 0 at A, getting 0 at B, right? Remember that event. Let's call that as some event number, let's say 1. Now, what is this event? Getting 1 here and getting 1 here, okay? Let's call it as 2 event. This is 1 event. If E11 occurs, that means both are getting 1 and 1, right? Otherwise, yeah, fine, it's okay, right? So E11 is about getting 1 and 1, and E22 is nothing but getting 2 and 2. Whenever event 1 occurs, 2 will not occur. Similarly, when 0 occurs, then 1 won't occur, because when you toss the coin, either head will come, otherwise tail will come. Both at a time cannot come, right? That 2 events, getting the head and getting the tail, they are mutually exclusive. Similarly, here also all these events are mutually exclusive. Now, what is my probability? What I want? I want probability for getting the collision. What is the probability that I get collision? I am calculating. To get the collision, event number 00 should occur, otherwise event number 11 should occur, or E22 or E33. Since all are mutually exclusive, remember one thing: when you have an event called, let me erase this one. Our event is this one, collision event. When collision will occur, the probability for collision, for that this should occur. The event name is E00 union E11 union E22 union E33. Correct? And you know the meaning of E00 event. E00 event is nothing but getting 0 at station A and getting 0 at station B. Correct? For that we know the probability. Now let's write the formula for this collision probability. Collision can be represented as this set of events E00 union E11 so on. Then the probability of that event is equal to E00 union E11 union E22 union E33. Already I told you that all these events like tossing the coin and getting head and getting tail, that means mutually exclusive. Whenever you have union of some exclusive events, then the union of the probability of all that events union is probability of E00 plus probability of E11 plus probability of E22 plus probability of E33. Since some of the students get confused about this mutual exclusiveness, I will tell you with coin. Example, let's say you have a coin and that we have, let's say, head and tail. So other side is tail, this side head. What is the probability that you get head? 1 by 2. What is the probability that you get tail? 1 by 2. These two are called events. Event. Getting head is an event. What is the probability that that head event occurs? 1 by 2. The probability that tail event occurs is 1 by 2. Now, let's say that event H is nothing but getting head, ET is nothing but event called getting tail. So, probability of H is nothing but probability of EH, probability of ET. Now, I want to have an event called EH union ET. That means what I am expecting? I am expecting an event called getting head or tail when tossed, a coin is tossed. Then further probability is probability of EH union ET. Now whenever you apply addition, don't blindly add. It's like sum rule in our discrete mathematics. We apply sum rule only when that events, tasks are, otherwise sets are mutually exclusive, isn't it? In the same way, if these two events are mutually exclusive, then only we have to add. Whenever there is a union, don't add them blindly. Ask that events are exclusive or not. My dear event H, what is you? So he is nothing but getting head. Whenever you toss a coin, if this event occurs, getting head, definitely tail event won't occur at the same time. That's why these two are exclusive events. Then blindly we can add. Remember, that is the principle of probability. Okay, probability of EH union plus probability of ET. Same way here. Now we are adding all that probabilities. Each probability is nothing but 1 by 4, 1 by 4. Already we computed. Then you get what? 4 times this 1 by 4 into 1 by 4, which is nothing but 1 by 4. That means with 1 by 4 probability, again there is a chance of getting the collision. Sir, what if one more collision occurs? Don't worry, this is a recursive procedure. So k value will become 3 now. So who is going to get k value 3? Because A and B are again involved in collision. So at both ends K value will become 3. Now we will try it again. This time what happens? So A is going to generate a random number between 0 to, it's a closed interval, 0 to 2 power k minus 1, 2 cube minus 1. That means 0 to 7. So here B is also going to generate a random number between 0 to 7. Now there is a very rare chance to get again collision. Why? If A picks 0, B should pick 0. A picks 1, B should pick 1. So that probability will be definitely lesser than the previous one this time. So there might be no collision. In that way, so this backup algorithm will be continued. Sir, every time there is a collision, then this K value will be incremented. See, so we are taking the range from 0 to 2 power k minus 1, right? That means the time slots we are distributing like anything. That means we are saying like this. Whenever K value is increased, then we are saying that, you know, my dear A, you pick here. My dear B, you pick here. In that way, we are distributing their timings so that after some time definitely they will succeed. Understand? So this is about binary, you know, backup algorithm. In binary backup algorithm, so we are going to use this technique. Understand? Now we'll see one numerical problem related to this algorithm. Okay, let's solve one gate problem related to this binary backup. Before that, I would like to add one more point. So for every variable or every station, there will be one variable called k. Okay, so k will be 0 initially. What I want to tell you is, so they are going to play a race like this, backup race. Now if A and B try, and if there is a collision, then k will be incremented to both of them, right? K equal to 1, k equal to 1. Again if they try, then if they again they get collision, k value will become 2 and this k value will become 2. Assume that, let's say, this time, third time what happened, A and B and C are again in the game. This time C is also added. C wants to send the data and B doesn't want to send the data because of its number it is getting postponed. But A immediately wants to send the data because of this k number. Okay, then again because of A and C's try, there is a collision, let's say. Then what is the number A gets? A gets the 3, remember it, because this is the third successive collision for A. What is the value C gets? It is not 3 because this is the first time it is getting the collision for the particular frame. That's why k value will become 1. Now B's k value will be 2 because it was not participating in this collision, third collision. Okay. Now again if they try, this time A and B again collide, then this value will become 4 and k value will become 3. Understand? Now suddenly what happened? So after these many collisions, everything, A successfully transmitted its frame, let's say. Okay. Now if A successfully transmits, then we have to make this k value to him 0 again. Then k starts with 0 again for A and B and C will have same values. Once they successfully transmit their frame, their k value will be again initialized to 0. By that time this k will be keep on incremented, remember it. Now we solve this problem which is asked in 2004 paper. A and B are the only two stations on an Ethernet. Ignore what is Ethernet everything now. That doesn't matter now. Each has a steady queue of frames to send. Every station has steady queue means actually so sufficient. That means, you know, this is, let's say, queue of a station A. So network layer is giving the data, A is sending the data. Network layer is giving the data, A is sending the data. In that way, inflow, I can say that network layer gives data which is inflow and data link layer is going to send the data outflow. That inflow is equal to outflow, then we say that that is steady state usually, right? You know that. So now we have a steady queue of frames. That means we are getting X number of frames, we are going to send X number of frames. That is the way we are maintaining. That is enough for us. So there are two stations. Now read the remaining thing. Both A and B attempt to transmit a frame. Fine. They have a frame and collide. Yes, there is a collision. We know that whenever there is a collision, this k value will be incremented to 1 everywhere and for every station which involves in the collision. Now, and what happened is A wins a back of race. That means we know that there will be a back of race, correct? A generates a random number between 0 to 1. B is also going to generate a random number between 0 to, remember, 2 power k minus 1 is the maximum number, 0 to 1. Okay, now A has 0, 1 possibility, B has 0, 1 possibility. But why A wins the race? What could happen so that A wins the race? Definitely A would have taken 0. That means A's computer generated a random number 0 and B's computer generated random number 1. Then only it happens A will win the game. Why, sir? Why not A equal to 1 and B's k value 0? Then B is going to wait for 0 into that random amount of time t. A is going to wait for 1 into t time. Then 0 into t means what? B is going to wait for 0 time. Then B will immediately send the data. A will wait. Then who will win? Definitely it means B is winning the game. Winning the race means that whoever wins the race, they are going to immediately send the data. That's it. Now that is over already. Now A already sent it. And successful transmission. Whenever it is successful transmission, then case variable will be initialized to 0 again. But bad luck is B is still having its frame with it. Correct? K value 1. Now read the remaining thing. Both A and B attempt to transmit and collide. Sorry. At the end of this successful transmission by A, both A and B attempt to transmit and collide. Maybe A has another data. Now A brought another data. Let's call X. B has the old data OLD. Now they are again trying. This time again, there is a collision. It is the second collision for B, and for A it is now first collision, isn't it? After successfully transmitting the frame, it is the first collision. So that's why K value will become this time 1 for it, and K value for B will be 2. That is the difference. Why case value is 2? Because while sending one particular frame, it is the second time B is trying to send the frame. So it's a second collision for it for a particular frame. That's why A is going to generate a random number between 0 to 1. B is going to generate a random number between 0, 1, 2, 3. 2 power k minus 1 is 3. Now the story begins. The question is the probability that A wins the second back of race. We will see. This problem can be solved in two ways. So first of all, the method number 1, just common sense. So you tell me what are the possibilities we have for A winning the game. Definitely for that we'll see the cases. What if A choose 0 and B choose 0? It will be collision. It should not happen because A should win the game. For that either B should pick 1 or 2 or 3. I am listing out all possibilities. So 0, 1, 0, 2, 0, 3 are the possibilities where A definitely wins the game, because A is sending immediately, B is waiting for 1 slot or 2 slots or 3 slots. Now what if A picks 1? We don't know, right? That is also possible. When A picks 1, then B should pick what? So that A wins the game. Our final goal should be A should win the game. For that B should pick a number which is greater than 1. That is obvious, right? Sir, what if B picks 1? There is a collision. Then A cannot win. So that's why definitely B should take either 2 or B should take 3. Now the next case. What if A picks 2? Is it possible? Impossible, right? Because A can take only 0 or 1. That's why this case never arises. Finally, we will see what are the favorable cases for us. 1, 2, 3, 4, 5. But what are the total cases? This is a simple formula in probability. Whenever you want to find out the probability for something, then for that event, what are the favorable cases we have and what are the total cases we have? If you calculate and if you divide one by one, you get the probability. And our favorable cases are 5. And how many total cases we have? How many different ways they can get the numbers? See, 0, 0, 0, 1, 0, 2, 0, 3. Now when A takes 1, again B can take 0, otherwise 1 and 2, 3. All these cases are equiprobable, correct? Anything can happen. So out of 8, 5 are favorable cases. That's why 5 by 8 is the probability. If you calculate 5 by 8 value, you get 0.625. In that way we can answer this question. Okay, this is method number 1. In method number 2, a little bit formal. That means we try to construct events. Okay, we will see that. The second model is like this. We write 2 events. Event number 1 is where this first component says that A gets 0. This event name is where A gets 0 and B gets, we write like this, event 0 and B 1 or 2 or 3. The meaning of this event is where A gets 0 and B gets 1 or 2 or 3. Otherwise, another event should occur. What is that? Where A gets 1 and B gets 2 or 3. Then only A is going to win the game. So we know that getting 0 for A and here A is getting 1, both are different events, are mutually exclusive events. That's why if you compute probability of these 2 events, then I can write like this. Let's use a small word for this one. Let's say X. This is Y. Probability of X union Y is nothing but probability of X plus probability of Y, because they are mutually exclusive events. Now what is probability of X? Probability of X is nothing but probability of getting this event where A gets 0, B gets 1 or 2 or 3. For that, favorable cases are what? 0, 1, 0, 2, 0, 3. Again story comes to same line. Okay, so 0, 1, 0, 2, 0, 3 means 3. Out of how many cases? 0, 0, 0, 1, 0, 2, 0, 3 and 1, 0, 1, 1, 1, 2, 1, 3. Out of that, favorable cases are, see, to occur this event 0, 1, 0, 2, 0, 3. Correct? I can say 3. 3 out of 8 plus what is probability of Y? Probability of this event occurring, right? What is that? Getting 1 for A and getting 2, 3 for B. For that we have only 1, 2 and 1, 3 cases, right? So out of how many cases? The total cases are again 8, we know that, right? I can say that 2 out of 8. All the cases are always 8. So 3 by 8 plus 2 by 8 is nothing but 5 by 8. If you simplify it, again you get 0.625. So that's why option B is the right choice. Okay.